Hey everyone, how are you? In this video, we are going to solve one of the hard problem of Leetcode, which is largest rectangle in histogram. In this problem, we are given the array of heights as an input, and these heights are the heights of different bars in a histogram. The output we need to give in the problem is we need to find a rectangle which is having the largest area. Now let us try to understand it with an example. So let us say the heights of different bars in a histogram is given as 2, 1, 5, 6, 1, 2. These are the different heights: 2, then 1, then we have 5, then we have 6, and then we have 1, and then we have 2. Every block or every bar is going to have a width of 1 and the height is given in the input. Now one of the rectangle which we can create for this particular example is this one. This is a rectangle, right? It has a width of 2 because we are considering 2 blocks. Every block has a width of 1. So considering 2 blocks, the width is 2 and the height is going to be 5. You can see that we are 1, 2, 3, 4, 5. 5 blocks are there. So the height is 5, width is 2, area is 10. Area is actually equal to height multiplied by width, right? That's simple. Now one more thing you need to understand is you cannot just choose these 2 blocks and create a rectangle of height 6 because you will have this missing piece, right? This will create a shape something like this. It's not a rectangle. That is, you need to understand that if you create a rectangle using different bars, let us say you choose 1, 2, 3, 4, 5. 5 number of bars to create your rectangle. So it will have a width of 5. But the height will be the minimum height of all these bars. So you just need to simply understand that if you choose multiple bars to create a rectangle, you will choose multiple bars to increase your width. More number of bars, it means better the width. And you need to find the rectangle which is having the largest area. Area is composed of height and width. So you need the best height and the best width. To get more width, you need to choose more number of bars. But the problem with choosing more number of bars is, let us say you choose this particular bar, and this particular bar. So you can now create a width of 3, right? This is your width, which is 3. And this is the rectangle which is having a width of 3. But now the height is 1, right? You have a height of 1 and width is 3. So the area is 3 multiplied by 1, which is 3. You already have an area which is 10, right? Just by choosing 2 number of bars. And why, if you choose, let us say, these 3 blocks, so why is the height just 1? It is very simple to understand. You cannot create a height of 5 here, right? If you create a height of 5, 1, 2, 3, 4, these 4 blocks are missing, right? If you create a rectangle, or let us say you create a shape using these 3 bars, so how the shape is going to look like? The shape is something like this, right? Now you can take this particular rectangle, right? This is an empty area. You cannot increase your rectangle size, basically the rectangle height, because this is an empty area. So from here what we understand is, more the number of bars you are choosing, better is the width, but then your height is actually going to be the minimum of all these bars. Now let us understand a very important pattern here. Let us try to understand that pattern using this particular data. Let us say your heights are just increasing. Calculating the best rectangle area in this case is going to be very easy. If you have a rectangle, then this is the starting point of your rectangle. Basically, this is the starting bar. Maybe this is your bar, or maybe let us say this is your rectangle. Then you will have a starting bar. Then you have some more number of bars here to increase the width. And then you will have an ending bar, right? Basically, if this is a rectangle, then this is the starting bar. This is the ending bar. And these are the blocks you have chosen, or the bars you have chosen. 4 number of bars, it means 4 is the width and the height is 2, the minimum out of these, right? Now since we have considered a data in which the data is just increasing, what we can do is we can say, let me process each data once to calculate what's the best rectangle. And what I will do is I will consider this as my extreme left. If I am processing this, this is the extreme left. If I am processing this, this is the extreme left. If I am processing this, this is the extreme left. Basically the leftmost bar of my rectangle. Now how much width I can go? The more the number of bars, better the width, right? And now we have considered a rectangle, not a rectangle, but the histogram, where the heights are just increasing. And let us say this is my first or the leftmost bar in my rectangle. Then the height will be 1 because other heights are just going to increase, right? So I'm definitely going to create a rectangle of height at least 1. Height is 1. And what is the width? I will choose this element, then this element, then this, and this. Basically, this is my leftmost data in my rectangle, and I will extend till the rightmost. I will extend till the last, right? So I can say if my data is just increasing, I will consider this, then this, then this, then this as my leftmost data, and I will just calculate my width. I have the height. Height will be my current data height because the data is going to increase. The height is going to increase. So this is going to be the minimum height, right? The data on which we are right now, the data which we are trying to process as of now. So for this one, the height is 1. The width is going to be 1, 2, 3, 4, 5, right? Multiplied by 5. The area is now going to be 5. This is one of the possible rectangle, right? Basically, this is our rectangle. The height here is 1. The width is 1, 2, 3, 4, 5. So the area is 5. How to calculate the height here? The height is simply your current data's height. And the width is going to be What's your extreme right? The extreme right index, let us talk about the indexes. Let us try to do it programmatically. How can we calculate the width? The indexes here are 0, 1, 2, 3, 4. My current index is 0, right? My extreme index is 4, and the total number of elements in our data is 5. But let me try to explain you the width calculation process with other data, not with this one. I will come back to this particular data to explain you how can you calculate the width. But since this is the extreme left, let us skip this process. I will tell you how to calculate this. Now let us try to calculate the rectangle using this particular element. If this is your extreme left, the height is 2. The other elements are having height as 3, 4 and 5. The heights are basically going to increase. So you can create a rectangle of height at least 2. And the width is going to be 1 element, 2 element, 3 element, 4 element. We are not going to extend in the left side. We are just extending in the right side. So the width is 4, 1, 2, 3, 4 elements. And the height is 2 now. Basically this is our rectangle. 2 and 4. 4 multiplied by 2 is equal to 8, right? Height is 2, width is 4, this is 8. Now how can I find that this is the width? 4 is the width. Basically how many elements do you have? You have 5 number of elements. What's the index of my current element? It is 1. What's the element just before 1? It is having the index as 0. I can say 5 minus 0 minus 1. And I will tell you why this formula is going to work. Basically here 5 is n. N is the number of elements. 0 is the last element's index. The element just before my current element. And I will tell you the reason for this. But first of all, try to understand the formula. N minus, let us say the last index is whatever is the last index. It is 0 as of now, minus 1. We have 5 elements, right? I am saying I will exclude all those elements which are before 2. If I don't include all the elements which are before 2, then that will tell me how many elements I have including 2 and after this. And that is what we need to find out, right? We need to find out how many elements do I have including this 2 and all the elements in the right side of 2. Basically, I want to find out how many elements I have. I have 1, 2, 3, 4 elements. So the total number of elements are 5, that is n number of elements, minus what is the index of my last element? It is 0. Because the indexes starts from 0, if I just say n minus last, so this is going to be 5 minus last index is 0, this is going to be 5. It is telling me that I have 5 data excluding all the data which is left to 2. But no, I have 4 data, right? I have 1, 2, 3, 4. So I have to say minus 1 because the indexes are starting from 0. So this is how we can calculate the width. I will come back to this particular input to explain you how this particular input and understanding its pattern is going to help us solve the problem. Now let me say that this is my extreme left of the rectangle. If this is the extreme left, since the data is increasing, I can extend my rectangle in the right side. I will have a height of 3, right? 1, 2, then 3. The height is 3. The width is 1, 2, 3. So I can say height is 3, width is 3, the area is 9. We got an answer of 5, then we got a better answer of 8, then we got a better answer of 9. As of now, our best answer is 9, right? Again, we know how to calculate the height. Height is the height of my current element, but how to calculate the width? It is 5, that's the number of element, minus last. What's the last index? The last index is 1. So I can say 5 minus 1, minus 1. This particular minus 1, right? So 5 minus 1 is 4, 4 minus 1 is 3. 3 number of elements are there, which are including this 3 and in the right side. We have 1, 2, 3 number of elements. We have excluded these 2 elements. So we got 3 number of elements using this particular formula. Again, similarly, we can calculate it for 4 and 5 as well. For 4, this is going to be 4 is the height. How much width? It is 1 and 2. 2 width. Why? Because n is 5. Element just before 4 is 3. Its index is 2. So 5 minus 2 minus 1. This is equal to 2. The height is 4. The width is 2. 4 multiplied by 2 is equal to 8. So 4 multiplied by 2 is 8. And starting from this 5, if we create the rectangle, it will be 5. That's the height. But the width is 1. So it is 5. The best rectangle we got is having the area of 9. And basically this is our rectangle. And this is going to be the final output. Right? This is my rectangle. Height is 3, width is 3, the area is 9. So from here what we found out is, if we have a data which is just increasing, then calculating the area is a piece of cake, right? It is very simple. But the problem is we have a data which is 2, then decreasing to 1, increasing to 5, increasing to 6, decreasing to 1, increasing to 2. So we have a data which is mixed, right? It is not just increasing. But what we are considering is, if we say that this is the data, we are actually going to process each data once. Because the problem says that the constraint is high. The number of heights we can actually have in the input is 10 is to power 5. So we are going to have a big set of data. So we cannot just run 2 loops. We have to do it in a single loop, right? So we are going to process each data once. But the problem is, if the data is mixed, it is increasing, decreasing, increasing, decreasing, then I cannot say that this is the leftmost part of my rectangle. Let me process this data and consider this as the leftmost, because if I extend in the right side, I got a height which is less. The moment I get a height which is less, I cannot extend my rectangle of a height of 2. I have to say that my rectangle is going to have a height of 1, right? So basically, if you want to include this and you want to go in the right side to increase your width, then you will have to compromise with your height, and that is going to be your rectangle. and this rectangle is going to have a area of 1, 2, 3, 4, 5, 6. 6 is the width, height is 1, so it is 6. Yes, this is one of the rectangle which can be calculated, but that's not the final answer. That's not the best area. So how can we just process one input and try to understand what's the best area this particular input can give me? So what we can do is we can say, okay, let's process it one by one. And the moment I see a height which is less, I have to apply some logic. And that is the logic which you need to understand. That's the logic which you need to build. Till we are processing inputs which are increasing, it is fine. It is easy to calculate. But the moment I am getting an input which is decreasing than my previous data, then there is a problem, and that's the problem we need to solve. Let us say we have the first data is 2, right? Let me write the indexes as well. 0, 1, 2, 3, 4, 5. This is my current data 2. Let me try to process this data 2. I am saying that this is the height which is the leftmost height in my rectangle, and I will extend in the right side. I will extend in the right side, but how much I can extend, I don't know, because I know that the data is not just increasing. So as of now, I will not calculate this, but I will store this data somewhere, and let's actually store this data in something called as a stack. And I will tell you the reason why we are storing it in a stack. I could have stored this in a normal queue or a normal array or a normal list, but why are we considering stack? That's one of the important point of this particular problem. We got a height of 2. Let's not do the processing, but let's try to consider the next data which is having a height of 1. Now I will tell you what's the reason of this stack. We know that if we have a data which is just increasing, we can easily calculate the different areas and we can just return the maximum one. But the next data which I see is decreasing. We are using a stack to create a data which is just increasing. If the data is just increasing, then in the stack we have an increasing data. We can calculate the areas. A stack which stores a data which is just increasing or which is just decreasing. Maybe you can store some data like 1, 2, 3, it is increasing, or 3, 2, 1, it is decreasing. Then that is called a monotonous stack. That's a special kind of stack, and that's the stack we need to create. So the moment I see that the next data is actually 1, which is less than 2, right? I cannot say that now my stack is having a data 2 then 1, because I am trying to create heights which are just increasing. So what do you want to do? Do you want to say, hey, let me drop the idea of adding 1, let me not consider 1 at all? That's one way of doing it. If you do not include 1 in your stack, let's forget about 1 for some time, and we see the next data is 5, then I can say, okay, let me store this 5 in my stack. Then I see the next data which is 6, let me store the 6 in my stack. You see that the heights are increasing, right? The heights are 2, then 5, then 6. But now again I see a height which is decreasing, which is 1, so I cannot store it in my stack. I cannot store 2 in my stack, because even if I store 2, then my stack is not just increasing, it is increasing then decreasing. I need a stack which is just increasing, because then I will be able to calculate the area easily, right? But if you ignore this 1, that's like saying that I don't even want to consider this data. But do you have a proof that I do not even need this data to create a rectangle? No, we do not have a proof as of now. So we cannot just simply ignore this data. So there are two things I can do. When I was processing this particular data 1, I have two options. Either I include this 1 and remove this 2, and I say that I have a stack which is starting at 1. Or what I can do is I can say I will include this 2, this particular element in my stack, and I will ignore this 1. Either way, you will have to calculate what's the best rectangle including the element which you are ignoring. If you ignore the element 1 to store the 5 in your stack, then you will have to calculate what's the best rectangle this particular 1 can give me. Or if I remove this 2 from my stack, because now I got a lower data, so I will say, okay, let me remove this 2 and let me store this 1 in my stack. Then while removing, again you will have to do the same thing. You will have to create a rectangle or calculate a rectangle area which is including 2. We cannot just simply remove the element. We have to find the area which is including this 2. We are going to say, earlier we had 2 in my stack. Now I got an element 1. The moment I get a 1, I will say that I will put this 1 in my stack, but I will remove this 2. So as of now, my stack is just increasing stack, right? I mean, we have just one element, so it is just increasing. But I will calculate an area which includes this 2. I want to create a rectangle which has a height of 2. So I want to create a rectangle which is having a height of at least 2. Because I want to create a rectangle including this element. So the rectangle is going to have a height of 2. Now you might say that if I create a rectangle of height 2 and I try to extend this, this is going to have height of 1 and height of 1. So the best rectangle I could create is having a height of 1 and a width of 6, because we are considering 1, 2, 3, 4, 5, 6 elements, and including this element which we are actually going to ignore from our stack. But we don't really need to calculate it, because we are going to calculate the area of the rectangle with width of 6 and height of 1 later on when we are processing our increasing data only. As of now, I just need to create a rectangle which is having a height of 2, basically using this particular element. Now I know that my element cannot extend in the right side because it is having a height of 1. So I could just include this element, and that is going to be my height. Height is 2. And how much is the width? Width is actually going to be calculated using the same formula here. N minus last minus 1. What is the value of n here? the n will not be equal to 5 or 6, that's the number of elements we have. Instead, the n here will be the index of this particular element, which is 1, the element which is stopping us to extend my height of 2. So the width is going to be 1 minus what's the last data we have seen, minus 1. Now this is important to understand what will be the last data. For 2, we do not even have a last data, right? We do not have a left data. Earlier, when we were calculating it, let us say for 3 by 3, so for the index number 2, the last index was 1, right? So we can simply say n is equal to 5. The last index we have seen is 1 minus 1. That's our formula. So this is equal to 3. So including this element, we have 1, 2, 3, 3 elements, right? But if we do not have a previous element, we are going to consider the last as a minus 1. And let me try to explain you with this particular data. If this is 1, then the width was 5, right? We can say we are using this particular formula, n is equal to 5. We are going to use last and then minus 1. This should be equal to 5, right? If you calculate the value here, then the last will be minus 1. So basically it is 5 minus minus 1 minus 1. This will be equal to 6 minus 1, which is 5, right? That's what we have here. So if we do not have a last element, the last will be minus 1, so that our formula remains correct. So here this will be minus 1. So 1 minus minus 1, this will be 2. 2 minus 1, this will be equal to 1. So the width is actually going to be 1. The moment I am removing this element, I am saying that the width is 1, the height is 2, the rectangle area is 2. So I got a rectangle area as 2. That's one of the answer I have calculated, right? Now at this point, you need to understand that we have a stack, a monotonic stack, which is having one element 1. I have already done the calculation for 2, right? I have this in my stack as 1. Let me try to process the next data, which is 5. Alright, 5 is having an increasing height compared to my last data in my stack. So as of now, if I just put the 5 in my stack, then my stack is just increasing stack. Later on, we are going to calculate the value for increasing stack. But as of now, my stack is just increasing. Next, we are considering the element 6. Again, my stack is just increasing. So let me put the 6 here. But now I got a 1. The moment I get a 1, I'm going to say, okay, this is a 1. I cannot put it here in my stack because now my stack is not increasing. So I have to remove this 6. Just like I removed this 2, right? So I have to remove this 6. But before removing the 6, I have to calculate the area, the best area which this 6 can give me if I consider the height as 6. If I consider the height as 6, how much right I can extend? Simply I can just use the same formula which I did for 2. I can say the height here is 6, right? The width will be, what's the stopping index? What's the extreme index which is stopping me to proceed in the right side? The index number 4. This is the index number 4. In this case, we are using the value of n because n is equal to 5. The index number 5 is actually stopping me to extend further, right? I cannot extend further because we do not even have elements. Similarly, that's what we are doing here as well. The index number 4 is stopping me to extend this data, right? Extend this data more so that I could increase my width. So this is the stopping index. What's the last index which I have seen just before 6? So 6 is having the index of 3. The last index we have seen is 2. If you see in the data also, the element is 5, which is having the index as 2. So I can say 4 minus 2 minus 1. That's the formula we have. Extreme index minus the last index minus 1. N minus last minus 1. So the value is going to be 1. So we could say the area is 6 multiplied by 1. So we had an area of 2. Now we have an area of 6. So the best answer we have as of now is 6. But now I can say this is removed from my stack. So let me actually remove this from my stack and let me actually remove this from my data as well. We don't actually need to consider these two elements. I can remove this and I can remove this as well. But right now we are still at this particular point and still I cannot put this particular height in my stack. That's because if you see here, this will be 1, then 5, then 1. This is not increasing. So we have to do the same thing with 5 as well. So now our height will actually be equal to 5. What is the width? To calculate the width, this is our stopping index 4. Minus what's the last index before 5? It is index number 1. So I can say the width will be 4 minus 1 minus 1. So this will be 2. And now you will understand the magic of this particular approach. I could extend here at index number 3, which we are not having as of now, which we just removed from our visual appearance, but it is still there, right? It is having a height of 6. And it will definitely have a height at least 5, right? And that is why I am able to extend it till this particular point. I will not be able to extend it more to increase our width because this is 1. But I can extend this particular point here and I can create a rectangle which is having a width of 1 and 2 and the height is going to be 5. So the height is 5, the width is 2, the area is 5 multiplied by 2 is 10. So we had an area of 6, now we have an area of 10. That's the best answer we have. And now I can get rid of this 5, right? I can get rid of this 5 and I can say I have done the calculation for this 5. So I can remove it from my stack as well. And now I can put this element, this height in my stack. Even if the height is equal, you can put it because if this is 1, you can extend it here, right? If the height would have been less, if this would have a height of 0, then you will not be able to extend it. Again, if you consider the next element, the height is 2. So you will put it in the stack. So the height is 2. And now your stack is 1, 1, 2. The indexes of your stack are 1, 4 and 5. Now let us start calculating the areas for these three elements. Each of this element which is there in your stack 1, 1 and 2, you can extend them till the extreme right. You can extend it till the extreme right. You can extend this particular element till the extreme right, and you can extend this particular element till the extreme right. And that is the reason we are trying to create a increasing stack, increasing list of heights. And before we have removed all the different heights we had, height of 2, height of 5, height of 6, we already calculated what's the best answer we could have using these elements. Now using these elements, we can do the calculations again, and I can say if this is 1, I could definitely extend it in the right side. But we are actually going to process our stack from the last. First 2 will be processed, then 1, then 1. So when we process the 2, the height is 2. Can it extend in the right side? So the height will be 2. For the width, what's the last data you have seen? The last data you have seen is having the index of 4. So this will be 4. So you can say n is 6. So 6, n minus last index 4 minus 1. So the width is going to be 1. Basically this is a rectangle. Height is 2, width is 1. 2 multiplied by 1, it is 2. That's the area you have. But you have a better answer as 10. Alright, we have processed this 2. Similarly, you are going to calculate the area for this particular element. In this case, height is going to be 1, width is going to be n minus last minus 1, n is equal to 6, last is equal to 1, that's the last index you have, minus 1, this is equal to 4. So the best rectangle you are going to create is this one, right? Now don't worry, you might say that this is the best rectangle with this element. Don't worry about this. We are going to use this particular element, right? That will get us the best answer for this. Because we are not going to include this element in our rectangle, this will have a separate calculation. So for this element, you got a rectangle area of 4. And now when you try to calculate the rectangular area for this particular element, this is going to extend in the right side and also in the left side till the last left element. You don't have a last left element, so last is equal to minus 1 in this case. Your width is going to be 6 minus minus 1 minus 1. That's basically this particular calculation, and the height here will be equal to 1. So the area is actually going to be 6 multiplied by 1. The area is 6. You have a better answer as 10. So that is your final output. So guys, that's the complete approach to solve it. And I know this was very complex to understand, but the whole point of this problem was monotonic stack. And why can you think about monotonic stack? The reason is, if you consider just the increasing areas, the calculation is very easy, right? And why are we even considering this particular point? Because for any block, the height could extend in the right side only if the blocks are having height increasing, right? For every block, the height is fixed, right? So if you consider any block, your rectangle will have the height as fixed, or you will have an idea about your rectangle's height. But you can extend in the right, extend in the left to create a better width. Your area is height multiplied by width. So we need to increase both these pointers, height and width. Height is restricted, but the width can be increased. But the problem of increasing the width is it can only increase if the heights are increasing. Then only you can consider those elements. Otherwise, if the heights are not increasing, let us say this is 3, then this is 2, then this is 1, and you try to extend this, you will have to compromise with the height just to increase the width. So this is a simple pattern which you need to catch, that increasing heights means you can extend your rectangle, and that is why we consider this monotonic stack. Monotonic stack is all about storing increasing data. Now let me try to explain you the code for this particular problem. Simply you can store the value of result as 0 initially, then create a stack which is empty, and the value of n, which is the length of heights, the number of bars or the number of heights you have. Now simply run a loop in your heights for I comma h and enumerate your heights. So I is going to store the indexes, h is going to store the height. Now we are going to run this logic while we have something in the stack, but we are not going to have, initially we are not going to have anything in the stack. So this logic will run and it will store your current element in the stack. But we are running this logic, we are saying that while we have something in the stack and the last element's height which is there in the stack, if that is more than your current element's height, it means we are not having a monotonic stack. We have to remove some elements. So we are saying that the last element's height is actually equal to, from the heights array, let me pop the stack, let me get the last element's index, store it as a height. So now we have the height, because the moment we are popping the data, we need to calculate the best possible rectangle using that data. So that is the height. What is the left? Till how much left can we extend? What's the left? It means what's the last data before this particular data, before the data we just popped out. It is going to be from stacks -1, that is the last element in my stack. If we have something in the stack, because we have popped out the data, there is the possibility that there is nothing in the stack. So if we have something in the stack, we are going to get the last index using that particular stack, else it is going to be -1. And now we are calculating the width. I is our extreme point where we need to stop, right? So I, this is the index, the current element at which the height is h. So we cannot extend our height, this particular block of height, in the right side. So we are saying that is our extreme point I, minus left -1. We have the width, we have the height. We can just calculate the result, which is going to the maximum of current value of result and height multiplied by width. And after processing this, we are going to have some data in my stack. The stack is going to have just increasing data. Now we can just have the same logic, but this time the height is going to be calculated in the same way. The left value is going to be calculated in the same way, but the width will be calculated using n minus left -1, because now the stack is definitely going to have increasing data. Again, we can calculate the result, which is the maximum of current value of result and height multiplied by width. And finally, we are going to have the maximum area of the largest rectangle. Now you can submit this and this is going to pass all the test cases. You can find the solution of this particular problem in the description of this video. You can find the GitHub link and you can just go to that link and you can search for this particular problem and you will find the optimized solution for this particular problem there. And now you can see the solution is accepted, the runtime is really good, the memory used is really good. So guys, we have solved the particular problem and I know it was complex to understand, but try to give it some time, try to understand the patterns which we are following, and then you will understand why we are using this particular solution approach. And not only you will understand how can you solve this one, but you will understand a very important concept called as monotonic stack. Monotonic stack is one of the important concepts which you need to understand if you want to solve a lot of different complex problems involving increasing data or decreasing set of data. So that's it for this video, guys. If this video has helped you to understand the problem, the solution approach, then make sure that you hit that like button. And if you are not subscribed to my channel as of now, then make sure that you subscribe to the channel as well. And I will see you guys in the next video. I want to see you guys in the next video. Thank you for watching this one.